Hello everyone, welcome to this video. I'm Jinpei from Carnegie Mellon University. Today I'm going to walk you through our work, compression-aware one-step diffusion model for JPEG artifact removal. In recent years, learning-based methods, especially diffusion models, have achieved impressive results in image restoration. However, as shown in the video examples, when these models are applied to JPEG artifact removal, the results are far from ideal. We still see obvious artifacts and missing details. A key reason is that these models often ignore JPEG compression priors. Without such priors, it's difficult for them to distinguish between distortions caused by compression and the natural features of the image. Now, JPEG compression is typically controlled by the quality factor, namely QF. A straightforward idea is to use QF as the prior. But QF is just a single integer, and the information it provides is very limited. Moreover, as shown in the examples on the right, which we call explicit learning, models trained this way struggle to generalize to unseen compression levels. They cannot reliably separate the representations of the same image when the quality factor changes. To overcome these limitations, we propose a compression-aware view embedder, namely CAVE, as shown in the examples, which we refer to as dual learning. Our method enables models to clearly separate different quality factors. The details of CAVE are illustrated in this figure. It uses an UNet encoder to extract visual features from the compressed images. During training, we have two branches. The first one is the QF prediction branch, which we call explicit learning. Here, CAVE is trained to predict the quality factor from any given compressed image. The second one is the image reconstruction branch, which we call implicit learning. This branch trains CAVE to directly reconstruct the original image. We further demonstrate the effectiveness of this dual learning strategy. As you can see, when CAVE is trained with explicit learning only, it can separate the quality factors that appeared during training. But for those unseen compression levels, CAVE still struggles. This shows that CAVE doesn't really understand the underlying compressed process. However, when we combine explicit learning with implicit learning, CAVE can even separate unseen quality factors. This indicates that the model has truly captured the nature of JPEG compression, rather than just memorizing the quality factors it saw during training. Next, let me give you an overview of CODiff. CODiff is built on the pre-trained image generative model Stable Diffusion 2.1. It is designed as an efficient one-step diffusion model for JPEG artifact removal. To the best of our knowledge, this is the first work to introduce a one-step diffusion model for this task, while explicitly incorporating compression priors. Here is how it works. Given a compressed input image, we first use a VE encoder to project it into the latent space. Then the diffusion model reconstructs the latent representation, conditioned on the compression prior. Finally, a VE decoder transforms the latent back into the image space. For training, we adopt both perceptual loss and gain loss to further enhance the reconstruction quality. This table presents the quantitative comparisons between CODiff and several state-of-the-art methods. As you can see, CODiff achieves clear improvements across the board on both reference and non-reference metrics. We also provide visual comparisons. As you can see, CODiff is able to reconstruct images with much finer details while staying faithful to the original content. In addition, CODiff achieves faster inference, using fewer parameters and requiring less runtime compared to existing diffusion-based methods. We also conduct comprehensive evaluation studies to validate our method. Specifically, we test CODiff with different prompt embeddings, including an empty string, learnable embeddings, and DIP from the CSR paper. From both the quantitative results and the visual comparisons, our CAVE module shows clear advantages over these alternatives. For the dual learning strategy, we also provide quantitative comparisons against using only explicit learning or only implicit learning. Our dual approach performs better across multiple metrics and datasets. Interestingly, we also look at the accuracy of predicting the quality factor. Even though explicit learning is designed specifically for this purpose, dual learning actually achieves higher accuracy. This shows that combining the two strategies not only helps reconstruction, but also strengthens the model's understanding of JPEG compression itself. In summary, we propose CODiff, a novel and effective one-step diffusion model for JPEG artifact removal. With the design of K1 of our dual learning strategy, we are able to better capture compression priors and achieve state-of-the-art performance. If you would like to learn more, please feel free to visit our poster session. I have also provided the open source code and my personal homepage here. Thank you for watching, and I look forward to discussing with you.